All right, guys, so let's look at this bell work. If you didn't complete it before, or if you did, whatever the case, let's just look at it real quick. So we've got, I mean, you should have read it by now, but essentially we've got a binomial situation that you are looking at a binomial because if we're looking at, oops, I'm not writing yet, bins, these are Bernoulli trials because they are binary, they're independent, they have the same probability, but they are specifically binomial because we have a set number. We're going to look at 30 applications, figure out the expected number that are going to be declined or turned down. And the mean of a binomial distribution for random variable x is n times p. In this case, it's the probability of being rejected. If 85% are approved, then 15% are rejected. It's going to be 30 times 0.15. So that's it. It's pretty straightforward. I mean, calculations in this class are always fairly straightforward, but it's the concepts and figuring out exactly which formula to use. That's where things can get a little bit tricky. All right, so we are going to be looking at the actual calculations when it comes to this right here. And here we go. On the following page, we're going to see the 10 most recent polls. I say most recent as of sometime in the fall. But there are 10 polls from Iowa in the presidential race. And you're going to just look at your birthday month, pick out which poll that you're going to be using, and just copy that down the data for now. So you're not going to know what to do with it yet. So just look at this, and we are going to work through the steps to find a confidence interval. So just write down your relevant data. And yeah, to make it specific, we're going to focus on one proportion, which is Trump's vote share. So right here, my birthday happens to be in February. So the only thing I need to copy down is those two pieces of information right there. And I'm doing this so everyone gets to calculate their own confidence interval, or, you know, it's unlikely you're going to be sharing that with too many people.
But not Biden.
Huh?
Just not Biden.
Not Biden, yeah. You can ignore Biden's percent share. All right, we don't have to spend too long with this. I'll just give another 30 seconds or so to make sure everyone's had the opportunity to copy down what they need. Okay, so this is what we were looking at yesterday. I already gave you these couple formulas that we've got. The point estimate plus or minus your margin of error will be your confidence interval, and that's the very generic formula. Now we're going to have another kind of generic formula here, but a little less. It's the statistic plus or minus a critical value times the standard error of the statistic. Okay, that's pretty good to know. All right, the point estimate is already known from the data you just wrote down. So specifically, the point estimate is that actual percent vote share that was predicted for Trump. So that first number you wrote down, in my case, 48%. So that's your point estimate. That's always easy to get. And the rest of this falls into place pretty well, so that's not a big deal. As we go through the process of calculating, keep in mind that we're mainly calculating the margin of error. Okay, and now this should hopefully look familiar to you. You've seen this formula a number of times. This is the formula for the standard deviation of a sampling distribution of sample proportions, I should say. But this assumes that we know the population proportion. And we don't really know the population proportion. Think of what a poll is, right? Like we talked about yesterday, it's making a prediction about something that we haven't gathered data on. And so we can't say, oh, well, the true proportion is point whatever. So we can't use this formula. Luckily, the formula that we use is pretty much identical. And it works exactly the way that you'd expect. If we don't know the true population proportion, the best we can do is use our sample proportion. Okay. And since we're only working with one sample, we aren't finding the true standard deviation for the sampling distribution. All right. Instead, we are finding what's called the standard error. And think about that name, the standard error. This how do we say this? The standard deviation means this is in the data set, the specific value that you get might vary from the mean by a certain amount. Well, the error here represents the difference from the sample mean, the mean of our sampling distribution. But the standard error is how big of a difference from the mean might we expect on average. And the error here is the built-in error that we get just by sampling. So I don't know if that explanation made any sense or not, but we do have a difference in terminology. So it is important when we use the sampling or the sample data to come up with our standard deviation. It's no longer a standard deviation. Instead, it's a standard error. So as long as you can understand that there's that notation, then you're good to go. It doesn't change much by way of calculation. Okay. So yeah, go ahead and do write this down. It is essentially the same thing. It is on your formula sheet as well, which everyone in the class here should now have. If you choose to get it out or not, that's fine. You can still write this formula down. Okay. Well, let's give about 15 seconds on this. Okay, I'm going to assume everyone's good to go with that, and I can remind you of it if you forget. So we're going to construct a model of a distribution. So this is made up data. No one has this, but pretend that Trump's vote share in the poll was 44% and 780 people were included. Therefore, you have this calculation. So you take your p hat, which is 0.44, 1 minus p hat right here, and then divide by the sample size, and there's your standard error for that particular model. All right, that's pretty straightforward. If you want to go ahead and calculate what you have already, you can, but we're going to come to that. All right, so the distribution model could look like this. So you have your p hat right here. You've got your standard error. So you would expect, within one standard error of the mean, that you would be, somewhere between 0.42 and 0.46. All right, that's hopefully pretty straightforward. Now, we are using a sampling distribution in reality assumes that we know the true population proportion and sample size, and we only have 1 point estimator, not a true proportion. And so this model is not exactly the same as the sampling distribution, but we're just looking at it to help us understand what the confidence interval is all about. All right, so it's one of these things where there's just like small little distinctions between, oh, well, this is based on a sample, so therefore it's not a true sampling distribution. But that's a little nuance that in the end, it won't matter because we don't really set up a model like this too much. Okay, so this will help understand what a confidence interval is all about. All right, so we've already seen this. Our margin of error is a critical value times the standard error, and we already have the standard error now. So there you go. You're 2/3 of the way there. We know what the statistic is. We know what the standard error is. And I should point out right now, the standard error calculation will change based on what type of data we're given. All right. So that's why they give you a very generic formula in your formula sheet, a very generic statistic right here, because these will change. The critical values will change as well, but those are a little bit more consistent. So what is the critical value? This is the question. Let's go back to the empirical rule. And we've talked about this so many times, you should have it memorized pretty well. So you know the empirical rule, the 68, 95, 99.7 rule. Well, the rule works pretty well, but it's not exactly correct. So the way that data truly falls in a normal distribution looks like this. And you can see specifically these numbers down here: 68.2, 95.4, 99.7. So the 99.7 is still accurate, but we call it the 68, 95, 99.7. It's not exactly 68 and 95. So as we are turning to critical values, this distinction between 68 and 68.2% will matter. Okay. So the critical value is the number of standard errors to move away from a point to a point estimate to correspond to the confidence level. And it's referred to as Z star. This is very much like a Z score. And in the past, we would have said 2 standard deviations away is 95% of the data. But what we just learned is that, and I'm jumping ahead a little bit, it's not exactly 95% of the data if you move 2 standard deviations away. So when we talk about moving 2 standard errors away, it's not going to capture 95% of the data. It's going to be a little more than that, 95.4%. Okay, and you can see kind of a distinction here. So the distinction, I'll just bring it back up again. Z star is specifically the critical value, and it tells us how many standard errors we need to move from a point estimate in order to create a confidence interval. Okay. So if I'm going too fast, if you want to see any more of that, you can stop me at any point. So we can calculate the critical values for any value on this, and luckily the AP formula sheet gives it to us here on table B, and I know you can't really read that very well. Well, you probably can read it well enough, but I'm going to zoom in right here. Now you can see it very clearly. Luckily, your confidence level is down here. If you have the actual physical copy of this and you want to look at it there, you can, but it is on screen also. So the confidence level is mentioned down here, C. And notice you've got your percent. So, based on the problem, you can find it really quickly. The only row that matters is the bottom one, because table B has a lot of different values, and we're going to talk about those another day. But for right now, the only row that matters is this one at the bottom that says infinity. And we'll talk about what that means. It says at the top of the column that those are degrees of freedom. We're going to talk about those another day. Okay, so assuming everyone's good, now we can find our critical value for specific confidence levels. Okay, so that's pretty much it. So where did these critical values come from? And let's refer to the model, okay? Oh, actually, I don't want to do that yet. So the model that we created looked like this, right? So this is basically a sampling distribution, and in our specific example, I think it's 0.44, and then our standard error was 0.0178, if I'm remembering correctly. So we got our different standard errors moving out. Now, the reason we talked about the critical value or the empirical rule, and we said that this 2 standard errors away is not really 95%, it's 95.4%. That means 95% is going to be, and I'm going to exaggerate this for effect, it's really a little bit inside those bounds. So there's 95.4% would mean go out 2 standard deviations, 2 standard errors. But 95% really is going out slightly less than 2 standard errors away. And if you look right here for 95% confidence level, instead of going out 2, I'm going to go out 1.96. And that really does capture exactly 95% of the data. Is this making sense for you guys? Okay. Now, there is no confidence level for 68%, but notice right here, there's a 70% confidence level, which is pretty close to 1 standard error away. So that's about what you'd expect. And if you wanted we don't need to go into much of this more. If that's making sense, that's the same idea, that the critical values are getting you the exact amount to be exactly 98%, rounded off to the thousands. Okay, hopefully that I didn't lose you in that explanation, but there we go. So what I want you guys to do is find the critical values that we should use for each of the following scenarios. And you can feel free to write those in or shout them out or send them by carrier pigeon to me, whatever you'd prefer. So the purpose of this, well, I wanted you guys to be able to look at the table and figure it out, but that's not too difficult to do. But the purpose of this is I wanted to make sure it's really clear that when you're figuring out what critical value to use, the only thing that matters is the confidence level. I mean, we need to know this other information, but we don't care about it when determining the critical value. So that's all that matters. So keep that in mind. The story gets a little bit more complex with our means, which is why we're starting with proportions today. But there we go. We're all good with that. Okay, so now we are going to make our calculation more and more specific. All right, rather than just having statistic, critical value, standard error, we're going to substitute in the specific values that we're using. And our specific formula for this calculation is going to be p hat plus or minus our z star critical value times the standard error calculation, which is just copied right there. We are going to have different types of critical values, and so that'll be important to get that part right. But for today, it's all z star. And this is called the one sample z interval for p, or a one proportion z interval. And right now, that's kind of a weird name. And if at this point you don't remember that name, that's okay. It's going to make more sense when we add more and more inference tests. In fact, this is your very first inference test right here. So we're going to have a total of, I don't know how many, 10 or so by the time we're done. So there we go. We got all that. That's good to go. And now we can find the margin of error with the following. And so the margin of error, remember, that just represents everything after the plus or minus. And there it is. So the critical value times the standard error. So, I mean, that's important to kind of recognize that that's the margin of error in case you have a problem where you need to use that. And we're going to have some examples why that would matter starting right here, or actually starting in a second. So let's go back to that data you copied down at the beginning. Now you have everything that you need. We want to calculate a 95% confidence interval for Trump's vote share in the November 2020 election based on your polling data. So I will pause and let you guys calculate that. And I want to jump in real quick. I'm not going to ask you what you got for your answers yet, but just to jump in real quick, my only question is, how are we supposed to present our answers? There you go. It is an interval, and you guys learned about intervals right here, and we can just present it this way. So you're going to have whatever your lower number is right here, and then your upper number right there, and that represents the interval for your confidence interval. There you go, if that made sense. So for this, we know it's going to be 0.4331 and 0.5629. Now, I do not have all of the confidence intervals calculated. And could you guys put up on the screen just somewhere what you calculated for your confidence intervals? So we should have at least a few different months. I don't expect we're going to have, well, we guaranteed won't have all 12 months represented. So just as many of those as we can get.
I got some bigger numbers. I got smaller numbers.
Okay. Well, hey, we can confirm this. It's worth it to go through, and we can just pick one of them. So 0.65 to, okay, so.
Wait, do you want me to write the answer for the whole thing, like the two of them?
Yeah, if you can also put the interval up there as well.
I'm sorry, I missed.
No, that's fine. You can take up the rest of the screen for that.
My apologies.
All right. And it's good that we're going through this because we can look at some of this data and we can calculate it right here just to make sure we're going through the formula correctly. I didn't give you much by way of like, here's step by step what to do. So I can understand.
So Leo and I switched iPads so I could charge you. So I used his answer.
Okay, Eli wanted to make sure it's very clear that this is not his answer. That's some confidence. No pun intended. We just happen to be talking about confidence.
You could have gone up for some shenanigans.
Man, we're not getting too many responses here. Maybe we're just not feeling super confident with this yet.
I don't think I got one right.
Okay, that is fine. That is fine. We can build up confidence by. I'm just going to run through the calculation I did for my particular month. So my numbers were. I'll do this up to the side. I had 0.48 as p hat, and my sample size was 435. Now, the good thing is I can just do this. When it asks to calculate the margin of error, that's just this part of the equation. So as soon as I solve that on the right, I can say there's my margin of error. All right, pretty straightforward. So my p hat is 0.48 plus or minus. And notice I'm actually just substituting into that formula right now. So it's going to follow that format. My Z star, because it's a 95% confidence level, is going to be 1.96. And now it's just the standard error calculation. So that's going to be 0.48, which is p hat. 1 minus p hat is 0.52. And divided by the sample size of 435. And that was the data that I copied down at the beginning. That's where it's coming from. Now, I'm not going to go through the step-by-step on that calculation, but as far as plugging the numbers in, now I can just take this that's on the right side of the plus or minus, plug that in my calculator, and I got, just like Lily said a few minutes ago, 0.0469, rounded to the 10,000th place. So there's the margin of error. Your numbers are going to be different, but you'll still plug them in the same spot. And so you'll get maybe a slightly different margin of error. If you have a bigger,
I figured
if
it
you-
out. I used the wrong key.
oh, okay. Oh yeah, no worries. If you have a bigger sample size, you're going to find that your, I can't think and talk at the same time. If you have a bigger sample size, you're going to find your margin of error is smaller than this. Some of you have, if you have birthdays in the right month, some of them were sample sizes of like 1,200 people. So in that case, you should have a margin of error that's closer to like 2% rather than 4.5%. Okay. And actually, we're going to come to that in just a minute. So now I can actually just do the plus and minus, and I do those calculations separately. I do 0.48 plus of 0.0469 and then 0.48 minus 0.0469. And that's where we come up with these numbers that are already shown right there. And so these are for March. So the one thing is right here, our upper value should be probably something different. I don't know if that was your margin of error. So we'll add that to the point estimate. So what was your point? What were actually, yeah, for March, let's look at those values. So what was your p hat? $43.
I think I just didn't do the plus or minus. I only did the plus.
There we go.
That's why I got 0.465.
There we go.
The other one, I just didn't.
Okay, so that would be 0.395 if we subtracted it. So really, I'm going to erase my work right here. So I have some room to show this. So in that case, if you have 0.43 with a 0.035 margin of error, then that would be 0.395 to 0.465. Is that working now? All right, and this can just be the margin of error. Okay. All right, so we don't need to see too much more than that, but hopefully just the process of going through this isn't too bad. You've been working with standard. This is essentially a standard deviation calculation. There's really no difference. And, you know, we're just now multiplying by a critical value. So this is essentially saying, instead of going out one standard deviation, one standard error, I want to go out almost two. And this total distance, you know, is 2 times, well, not 2 times. Let's get it right. 1.96 times, that's a 9 right there, my standard error. And then that'll give me my 95% on the upper and lower end. And this represents right here 95% of the data. All right. So are you guys feeling like this is making sense, or have I confused things drastically? Okay, getting.
I would say that formula is pretty easy, but there's a lot of terminology which I still.
Okay. There we go. And so the comment here was that some of the terminology can cause things to get a little bit trickier, but the formula is straightforward. Okay. So we can just keep working with that vocabulary, and if something doesn't make sense when I say it, then, you know, feel free to jump in and like ask what it means when I say something in particular. So I'm going to clear this out. All right, and actually, let me undo that. All right, so we can see this prediction was going to be somewhere between 43 and 51%. This is going to be between 43 and 56%, but notice this margin of error is way smaller than the one that I had, which is 0.0469. And this one is going anywhere from 40% to 47% essentially. And there we go. That's how we can get all these different values. And 95% confidence means that 95% of these should capture the true population mean, the true population parameter. All right, so now let me clear that. Now we're going to move forward. We're going to see why it's helpful to look at the margin of error sometimes. I can't guarantee you're going to have a problem like this on the AP test, but I could say that it's somewhat likely that you will. I have 90% confidence that you will see a question like this on the AP statistics test. You're about to create a 95% confidence interval for proportion of voters who prefer Biden, but you don't want a margin of error greater than 3%. How many people should be in the sample? This is a question, I'll tell you right now, you can answer this question when it comes to proportions. We cannot have a question like this when it comes to means. All right, and we will learn about that more when we look at means another day. So my margin of error, I want to be no greater than 3%. So I have a formula for margin of error. And if my limit is 0.03 on the margin of error, and it's a 95% confidence interval, well, we already know the Z star for that is 1.96. So now the question is, how big does my sample size need to be? Well, and now we run into a problem because I also don't have a p-hat or a population proportion to work with. So what should we pick if we don't have anything to base this on? Any thought? No, we would. That's a good thought. It's a good thought, but it's not going to be that. So if I don't have any p-hat given, and we haven't even done this poll yet, so we find our p-hat at the conclusion of the poll. We're setting it up ahead of time, and I don't know what the p-hat's going to end up being. So what should I make the p hat for the purpose of this calculation? Making you guys think here. We wouldn't want to go with 100%.
Is it 0.5?
0.5. There it is. Now there's a couple of reasons for that. If we don't know what the true proportion is, or what the p hat is going to be, then 0.5 makes it, yeah, it's 50-50. And so that's kind of a safe thing to use. But mathematically, there's a reason we pick that. Remember that we are going to multiply p hat times 1 minus p hat. And when we do that, 0.5 times 0.5 is the maximum that we're going to get from this. So that is going to be, this is actually a quadratic right here. And at 0.5 times 0.5, we're going to get 0.25. That's the highest value we get, 0.25. If I pick any other value, it's going to be less, right? So all the way down to this value over here. So this will be 0 and 0 at the ends. So 0.25 is the biggest value that we can have in the numerator. And we get that at the 0.5 level. And the reason that this matters is because if I have the biggest value possible right here, then that requires the biggest sample size in order to get the required margin of error. All right, so I'll say that again. I'm essentially making it harder to get a margin of error of 0.03 by picking this value up here. And if I make it harder, then this is the most extreme example of how many I will need in the sample size. And so as long as I can calculate this now, then any sample size that I'm about to calculate, any sample size that big, will definitely give me a margin of error of 0.03 or smaller. Okay, so hopefully that made sense. Keep saying hopefully that makes sense. Maybe I should just be a better teacher. I don't know. But now at this point, we can just calculate, and this, I'm not boxing that formula because you need to know it. I'm boxing that just to say this is what we're essentially going to solve for n at this point. And it's just algebra. So we can, I'm not going to run through the steps. You can figure out how to do that calculation. And I will come up with an answer, and you can come up with an answer. We'll make sure we all get the same thing. Now, I was able to get the same thing. So I will say that, at least according to what I found, that is correct. All right, did anyone, this is a weird thing to solve for. It's not the first kind of equation you'd ever be given in middle school. So it's a weird thing to solve for n. Did anyone get stuck along the way? We can go over it. All right, so essentially what I did here, let me get rid of this stuff, is I started by dividing by, I'm going to move your answer over. So I'm just going to erase that real quick. But we'll bring that answer back up in a second. Okay. So I started by dividing by 1.96. And I actually don't know what that is. Some weird like 0.0. I'm just going to, these numbers don't matter. I'm kind of keeping those stored in my calculator. So now that equals square root of 0.5 times 0.5. And actually we can go ahead and calculate. We know what 0.5 times 0.5 is. It's 0.25. All right, so probably good with this. What I did is I squared both sides. And so that gave me an even smaller number, which is essentially 2.34 times 10 to the negative fourth equals 0.25 over n. And then just doing a little switcheroo, and it's just kind of doing a double move here, I can say that n equals 0.25 divided by 2.34 times 10 to the negative 4. Okay, no worries. And now that gives us the 1067.11 and so on. So it's a good thing to go through that. Now, how many people should be in the sample? This is a key thing. How should I round this? We always want to round it up. Okay, and conceptually the reason is if I go down to 1067, even though it doesn't seem like a big deal, and in reality it's not a big deal, but just to be, exact, if I go down to 1067, technically my margin of error could be just above 3%, like 3% and the smallest amount, right? But if I go up to 1068, then it's going to be just a fraction below 3%. And so the sample size we should be shooting for is 1068 people. And the good thing about that number, like I was saying at the beginning, no matter what the true p hat ends up being, our margin of error is going to be less than 3%. If it is truly 50-50, then it's going to be right at 3%. If it's closer to like a 40%, 60%, somewhere closer to 10% away from that, then we're going to have an even smaller margin of error. All right. Any questions on this? Always round up. There we go. All right. Current estimates are that 35% of all people are registered Democrats. You're about to conduct a survey that, among other things, will find out if a person is a registered Democrat. How many people should be in the survey if you want a 99% confidence interval to have a margin of 2%? All right. Any thoughts on what we should do for this particular problem? I'm just going to put the equal. We're going to have an equation written down. Any ideas of what should go in that equation and where? Okay, but you do know we need the critical value for 99%. So that's good. I have to look. I don't know these either. All right. Can anyone find that and tell me what the critical value is? I found it, but I want you guys to have some fun too. Will I actually find it? That's not good. I wonder if someone just asked their phone what the critical value is. I've never tried that before. Anyone find it yet? Very close. Yeah, we would use 2.576. So on table B, it's 2.576. Now, this is not something you have. I mean, obviously, you will not memorize these critical values. Not all of them. You'll probably remember the 95% one, but you just need to know where to find it. And so I encourage you right now to get out your formula sheet or just have it on your iPad, something you can flip to pretty quickly so that you can find those. Okay. So there we go. We've plugged in our critical value. What else could we plug in?
The true value, the 35%.
All right, and here they do have a prediction of a p-hat, or it's a p-hat, but it's a prediction of the true population parameter. So we can actually use that. So there we go. So I will plug that in, 0.35 and 1 minus 0.35. What else can we plug in? There you go, the margin of error. Where does that go? There it is, the left side. So we're going to plug in the margin of error also. So now what they're asking is how many people. So it's the same calculation. If we want to run through that, we can. At this point, we've done the hard part as far as plugging the correct values in. Why not? Let's get some practice. Go ahead. See if we can all come up with the same answer this time. Okay. So notice that we got two different values here. And what I calculated was 3,775. And we got another answer at 3,838. And those seem really different. But I'm guessing the reason there's a difference here is because when this one was calculated, there was maybe they took a value and just truncated it. They rounded it off partway through the calculation. So essentially it's the same thing, but at a certain point I ended up with a value that was like 2.6496, times 10 to the negative fourth. That was the value I came up with at a certain point. And if you didn't copy all those digits down and keep it saved in your calculator, that's going to actually throw off your numbers pretty big. So anyways, but I think this is all good. All right, we're getting the hang of this. This is all pretty good. We've calculated confidence intervals, we've calculated margin of errors, and we've worked backwards to figure out what sample sizes need to be based on a margin of error. Let's see what we got here. So now we're going to talk about the assumptions of a confidence interval. We must meet certain conditions in order to be able to even do this. So you can't just rush ahead and just plug these numbers into a formula, call it good. First, we need to make sure it's even appropriate to do so. So the sample that we get these values from, it needs to be a random sample. And that's pretty straightforward. We need to meet the 10% condition. The sample size needs to be 10% or less of the population. All right. And the large counts condition must be met, which says that it will be, the sampling distribution created from this will be approximately normal. All right, so the 10% condition is here to make sure that we don't have to use any more complex calculations. There are ways of doing this where if you end up using more than 10% of the population, then you can account for that and make some corrections. But if it's 10% or less, we can just use simple calculations. That's the whole idea behind it. These conditions should look familiar, all right? And if they don't look familiar, then they will look very familiar in the next few weeks as we use these over and over and over again. So the large count condition tests for normality. So if it passes a large counts condition, then we can assume it's a normal distribution. And then all the calculations that we do based on this will work. Okay, so and the way we test that is n times p and n times 1 minus p must both be greater than 10. All right, now I'll go ahead and tell you with our polls data that we just used, there was no danger. We passed all these conditions, so that's good. All right, so now we're going to do some practice, and maybe we'll just do one of these. All right, 34. Okay, this is definitely from the fall, you can tell, because now this is moot. 34 of 85 people in a recent random sample of FHS students said that they prefer remote learning. Construct a 96% confidence interval for the proportion of FHS students that prefer remote learning. And when I ask this question, I don't want you to just jump right into solving it right away, because this is the very first time we're going to look at the format of how we might present an answer to this in order to have a complete answer for AP purposes. So we have kind of this format that we're going to follow. We're going to first of all state the parameter that we want to estimate and the confidence level. The parameter that we're trying to estimate is the true proportion of FHS students that prefer remote learning. And actually, I'm going to write it this way. I'm really trying to find P, which is the population proportion, and this is the true proportion of FHS students who prefer remote learning. All right, and I'll point out at the beginning, this is going to seem like a very intensive way of answering a question, but you will get more and more familiar with it. Okay, the confidence level in this case, 96%. So that's what we want to do first. We want to just state what it is we're even trying to solve. Next, we're going to identify the appropriate inference method and check conditions. So the name of the procedure, again, you probably don't even remember at this point. Does anyone remember what we call this procedure? I mentioned it a little while ago. So I can call this, there's different names we could give it, but I'm going to call this a one proportion Z interval. Okay. So I really don't want you guys getting freaked out if you're like, oh my gosh, we're expected to know all of this. And I don't even know, don't freak out about this right now. When we check the conditions, we need to check the random condition, the 10% condition, and the large counts, which is essentially our normality condition. So is this random? So that's an easy one to check. It's a random sample. I just go back up to the very top. It says it's a random sample. So yes. So I'm just going to put right here, random sample. If I want to be extra, imagine this is on paper, and this is actually what someone grading your answer is going to be looking at. Then, you could even do this. I could draw an arrow back to this. 10% condition. 85. Is 85 less than 10% of the population at Flag High? Yes, it is. We have over 1,000 students. We have over 850. So yeah, I can put that N is less than 10% of population. And then the large counts. This is where we do our N times P and N times 1 minus P. Well, in this case, P hat, because that's all we have. N times P hat. Well, we have to figure that out, don't we? Well, let me give you a spoiler. If we figure out the proportion, then we do N times that, we're just going to get 34 and 51. All right. So, but, we need to figure out P hat. So it's going to be 34 divided by 85. Which is 0.4. So again, now if I did this, let me go ahead and erase this. We'll do it again. So if I did 85 times 0.4, basically I'm just undoing that calculation I just did, and that's why it's going to give me 34. And then if I did 85 times 0.6, I would get the 51. Okay, so in this case, we met the large counts condition. Both of those are greater than, maybe I could do this. N times P is greater than or equal to 10. N times 1 minus P, P hat, I got to be careful here, is greater than or equal to 10. So we met those conditions. So we want to take the time to actually show that. If you do not show that you have checked your conditions, you will lose points. If the conditions are met, we can perform the calculations. Now, we don't just jump into the calculations. We need to, first of all, show the general formula. And the general formula is our statistic plus or minus the critical value times the standard error. And I know a lot of you might be thinking, it's like, these are a lot of steps. I could just plug this into my formula and be done. But again, this is to show that you have gone through the entire process of answering this question. Now we can put a specific formula for this confidence interval. The specific formula, because we're dealing with proportions, is going to be P hat, which is our specific statistic, plus or minus, it's going to be a z star for our critical value. And the standard error is given as p hat times 1 minus p hat divided by n, all under the radical. And like I've been saying a few times, when we have the interval that we create for means, we'll have a different specific formula to use there. And now we can, well, I'm not going to conclude just yet. That's the last part of this. What I can do now is I can actually do the calculation. So p hat is 0.4 plus or minus, and this is where I'll actually just do the work like you would have jumped right into at the beginning. 0.4, the z star, it's a 96% confidence level. So I need to figure out what the confidence, sorry, the critical value is for that confidence level. And what is that going to be? $2.054. I'm going to put this up on the dot cam, but I'm literally just moving over. I can't see where it is, but 96 is somewhere in this range. And as soon as I find 96, I'm just going to move up and see what that bottom row says. So 2.054. Thank you for that, Kevin. Okay. And then now we can plug in the rest of this, which is going to be the square root of p hat is 0.4, 0.6 over a sample size of 85. All right, we can go through and calculate from here. I'll pause the video. We can just do that. And let's come up with the confidence interval right there. Okay, now notice this confidence interval is pretty wide. It's wide for a couple of reasons. One is that we use the 96% confidence interval. It's a little bit wider than the 95%. And remember, we want 96% of all of these confidence intervals created to capture the true population parameter. So we're going to make the net, cast it a little bit wider. So that's why our interval gets a little bit wider the bigger our confidence interval is. But also we had a pretty small sample size. 85 is not that big. So now we have over a 20% difference as far as our interval goes. So you have a 10% margin of error essentially. And that's pretty big, but you know, that's the way it goes for this particular problem. So now we want to interpret this. We've got our confidence interval, and maybe I'll pause right there. Are there any questions on what we've done so far? All right. So I do want to point out these first two steps, even half of the third step, this is really just laying out all of the prerequisites and just setting out what information do we know, what am I working with, what test am I using, that kind of information. If you don't follow this format exactly, that's fine, but you do want to make sure you have this information presented somewhere. Like I'm solving for this particular parameter with an explanation. I'm using this confidence level. I'm checking my conditions. I'm using this procedure in order to get it done. And especially showing the specific formula that you're using and then showing the numbers plugged in, that's going to be essential. But it can be in a different format. I'm just going to keep us using this one. So anyways, let's jump to the conclusion now. The conclusion is always just a sentence or two. So we will write this one. We are, you can write it as a, a we statement. We are 96% confident that the interval from 0.291 to 0.509 captures the true, this is true, proportion of FHS students who prefer remote learning. All right, now notice the language from this, the first half of it is kind of the template that we saw yesterday. We are blank % confident that the interval from blank to blank captures the, and then the last part of it is, it comes from right here, the parameter that I said I was going to calculate. The true proportion of FHS students who prefer remote learning. So if you set that up at the beginning, then writing your conclusion of this is pretty straightforward. In this case, we only need to write one sentence. Sometimes for some of these tests, we're going to have to write 2 sentences. And when we get to those, we will learn that format. And again, I know it seems kind of formulaic and it takes some of the, I don't know, interest out of it. I don't know if there's interest, if that's the right word, but the reason I give you guys templates to follow is to make sure you phrase things the right way. Because if you just leave it up to your own, like how you think it should be phrased, then there's a chance you phrase something slightly incorrectly that doesn't make a difference to you, but does make a difference to a grader. So this is a way that you will not get in any trouble. And if you want, you guys can take a screenshot of this, and if you can read my writing, because we're going to see more examples like this. And it's good to kind of know what we're doing to fill in these gaps, to fill in these different blanks. So I'll leave that there for just another 10 seconds or so. If you do want to screenshot, you don't have to. All right. Okay, I'm going to move forward now. And I'm going to clear all my writing. Now, I'm going to save you from having to go through a second one of these today. We might go through another one of these. We might do this tomorrow or something. We'll see what the time is. But we can, what I encourage you to do is go through this example and see if you can figure out how to fill in all the blanks based on the example I just gave you, and so on. So here's your homework for this particular night. And there we go. I've spoken way too much today. So have a wonderful day. If you do have any questions, feel free to stick around, and I will see you guys tomorrow.